All right, so as promised, we're back again. I'm now on the link that's available in the PowerPoint slides, this radford.edu. It's a population genetics simulation program. The idea is we can simulate a lot of individuals producing a lot of offspring, and do this very, very quickly, whereas it would take us days to do this any other way. I'm going to work out here with a population of 5,000 individuals. We're going to allow the population to go out 200 generations. And as promised, here are the fitnesses of our three genotypes: homozygous A1, heterozygous, and homozygous A2. Okay, so I'm going to start out initially assuming that A1 is dominant and A2 is recessive. So I'm going to start out by saying that this dominant allele is not a very good allele to have. The recessive allele is much better. So I can go ahead and indicate that by altering the relative fitnesses of each of those genotypes. So here I'm saying that the relative fitness of the homozygous A1, that's the dominant, is 60% that of the homozygous A2, and the heterozygote has a fitness determined by that dominant allele because it's expressed in the heterozygote, and that's also 60%. Okay? Then what I'm going to do is start the allele frequency off at 50%. So I believe that this one here is going to plot the frequency of the A1 and A2 simultaneously. So we're going to plot both frequencies on the same plot. One color for dominant, one color for recessive. So the idea is the allele frequency is going to change through the activity of natural selection. The question is, how is it going to change? So I'm going to start at 50%, and I'd like you to think a little bit here about specifically what's happening to that dominant allele's frequency within the population. What's happening to its frequency? Do you expect its frequency to increase or to decrease? And if you expect an increase or a decrease, what do you expect the shape of that curve to be? And do you expect that curve to reach either 100%, meaning that all of the alleles in the population are now A1, or do you expect that all of the A1 alleles will be removed from the population and I would be left with just A2 alleles? Okay? If you take the A1 allele here, this is called fixation, and we say that we have fixed the A1 allele. Here, if we took it down to here, we would refer to this as fixation of the A2 allele. Okay? All right. So you've got your predictions, I think. Let's go ahead and run this and see what happens. So go down to this little go button, and boom, we can plot those out. The light blue is the frequency of the A1. Right? So this is the frequency of the A1 allele. And what happened? Well, very quickly in the population, the frequency of the A1 allele began to drop, and at some point here, 23 generations in, this curve hit 0. That is, we fixed the A2 allele, and we lost the A1 allele. Okay? Right, so it looks like if the allele is dominant, and having this allele reduces your fitness, right? We say that that allele is deleterious because it reduces fitness. if the dominant allele reduces fitness, what happens to its frequency in the population? Well, it disappears. Why? Because natural selection selects for the A2 allele at the expense of the A1 allele. All right. Okay, so let's work the next one. In our next case, let's make A2 recessive and A1 dominant, but let's have selection against the recessive allele. Our first case was selection against the dominant allele. Now let's do selection against the recessive allele. So to do that, we just say that anybody that has the dominant allele has a higher fitness than people that have the recessive allele. If you have 2 copies of the recessive, 60% of the fitness of individuals that have an A1. Doesn't matter if they have 1 or 2, do they have an A1? All right, so let's start off here by resetting, and then let's make some predictions. If I start the allele frequency off here at 50%, what is going to happen to the A1 allele? What's going to happen to the A2 allele? Will they increase, decline in frequency, and will I get fixation? All right, so let's go ahead and try it. Here's a go. Let's start it off. Ooh, very different from the one before that. Much different. It looks a little odd, doesn't it? Still running, still running. Hit the end of the curve. Which one of these is the A2 allele? Well, that's the dark blue. So fixation against an allele that's recessive. Very different condition than selection against a dominant allele. It looks like recessive alleles, natural selection has a hard time removing. In fact, even after 200 generations, the A2 allele is still in this population, even though it's not a very good allele to have. Well, why is that? Well, the A2 allele is being selected against, but natural selection can only select against it when it sees it. And it can only see it when it's in the homozygous condition. In other words, natural selection does not see the A2 allele in the heterozygote. We call this phenomenon masking. We say that the recessive allele is being masked or hidden from natural selection in heterozygotes by the dominant allele. Okay? Now, I also want to show you kind of what's happening in the population overall based on the frequencies of the genotypes, which it's actually plotted for us, but I want to do some math on it anyway. When we first started this population, if we assume that Hardy-Weinberg equilibrium is occurring, and I know we shouldn't do that because selection is operating, but it'll give us an idea of what is actually happening within this population. So at this point, what are the expected frequencies of the 3 genotypes? Well, the genotype that is the A1 is given by p squared, okay? And the frequency of the A times the frequency of A, so A1. Well, the frequency of A1 here is 50%, so that means that the frequency of the homozygous A1 at this point in time is 25%. And if you look here, that's exactly what the computer says. The frequency of the A1 at the start is 25%. What's the frequency of the homozygous A2? Well, that's given by this. That's also 25%, because it's 50% times 50%. The frequency of the heterozygote Well, that's going to be 2pq, which is equal to 2 times 50% times 50%, or 25%. Sorry, 50%. I did that wrong, didn't I? 2pq is 2 times p times q, right? That would be 0.5 times 0.5 is 0.25 times 2 is 0.5. And that's exactly what we predict for that first generation. Okay? Now, selection begins to work on this population. It's selecting against the A2 allele. And anytime individuals have this genotype, they leave fewer copies than individuals with this genotype. So the frequency of the A1 starts to increase, and the frequency of the A2 starts to decrease. But notice that the rate of decrease here is changing. Those of you calculus-minded, right, there's a change in the rate over time. Right? Here the rate is given by the tangent there, and the rate is changing over time. Okay? Now, let's look at the population when the allele frequency for the A1 is, let's say, 0.2. So if we say that the frequency of A1 equals 0.2, the frequency of A2, frequency of A1 is 80%, and the frequency of A2 is 20%. Okay? Right? At this point here, this many generations in, the allele frequency is 20% for the A2. Well, what's the expected frequency of the A1A1, the A1A2, and the A2A2? Well, we can get at that with the Hardy-Weinberg equilibrium. The frequency of the A1 would be 64%. The frequencies of the A2s would be 0.04, and the frequency of the heterozygote would be 16 times 2, or 32%. So we started out with 50% heterozygote, 25% A2A2. Look what happened to the frequency of the A2A2. Where are most of the A2 alleles now? Well, most of the A2 alleles are contained within the heterozygote, where selection can't see them. The more this goes on, the more A2 alleles get driven into heterozygotes, and less of them should be found in the homozygous recessives. So at an allele frequency of 90% and an allele frequency for the A2 of 0.1, the frequency of the A1A1 would be equal to 81. The frequency of the A1A2 would be equal to 9.18. And the frequency of the A2A2 is equal to 1%, 0.01, right? We're continuing as we go along to move the A2 alleles out of the homozygous recessive. They're still in the population, but they're hiding as heterozygotes. Natural selection cannot see these. Okay? The situation that we've just done here, this situation is basically directional selection. We selected against a particular allele to push the population in a particular direction. And we did two cases: selection against the dominant and selection against the recessive. When selection operates against the dominant, it appears to be able to remove that allele from the population very easily. When natural selection works against the recessive allele, it has a harder time because of masking. The heterozygote masks the presence of that recessive allele. Okay? Now, as an aside, those of you that are interested in kind of human genetics and human medicine, you could ask, well, there are particular diseases in humans that are caused by particular alleles. If I went out into the population, which types of deleterious alleles that negatively influence fitness, which type of deleterious allele would I expect to be more common? An allele that's dominant that causes the genetic disorder, or an allele that's recessive that causes the genetic disorder? And the answer is recessive. Because anytime a deleterious recessive allele is introduced into the population, right, natural selection wouldn't be able to see it initially because there's just one of them hiding in a heterozygote. And the idea is that there should always be a certain frequency of these deleterious recessives because selection can't get rid of them. On the other hand, dominant alleles are seen very easily by natural selection. They should be removed very quickly by natural selection. We should see fewer genetic disorders caused by dominant alleles. Now, having said that, there are a number of human conditions caused by dominant alleles, including chondroplasia. That's a form of dwarfism. So if a chondroplasia is caused by a dominant A1 allele, then why is it still in the human population if it's easy for natural selection to remove it? Seems like a fairly basic question. And the answer to that question is mutation. Because every time selection removes the achondroplasia allele from the population, mutation dumps it back in, selection removes it, mutation dumps it back in, and the rate of removal and the rate of introducing into the population, these rates balance out like a dynamic equilibrium to give you a finite frequency of these dominant alleles due to mutations. The recessive ones are being maintained because of masking. The dominant ones are being removed but reintroduced into the population all the time. Okay? All right. Now, since I introduced things to you this way, I said, well, directional selection. You should be immediately thinking, all right, if he's talking